everyone. Today we'll be talking about some phenomenon that happen with respect to light and light traveling through different medium. And so when we take a look at this example right here, what we're going to see is a situation where we can actually look through something and light bends, but we also get a reflection. And this particular phenomenon, and it's pretty creatively named, partial reflection and refraction. Okay, so the situations that you need for this to happen is that light is going to travel between at least two medium, and you're going to have to have light going from a slow to a fast medium as well. All right, so let's take a look. When we sit there and we try to define what happens when we see reflection and refraction, there's two situations that we have to consider. First, at what angle is that incident ray coming in? So for instance, is the sun coming in at a small incident angle? So that would be something like if we're talking about a high noon, perhaps, like when the sun is really high up in the sky, versus when the sun is setting or rising, when it's really low in the sky, and the angle of incidence would be very big. Okay, so, and in this situation, I'm kind of envisioning like a low sunrise or sunset over a body of water. Okay. Also, we've got to consider the index of refraction for each of the medium that the light is traveling through. So if you remember from our last lesson, index of refraction is n, and it's a way that we can use, it's a number actually, not a way. It's a number that we use to see how fast light travels in a certain substance. Okay, so the lowest index of refraction would be in a vacuum. And I know you've already done this, but I'm just reminding you. It's a vacuum because there's nothing to slow that light down. Okay, so if you think of light as something that's moving, there's no friction. There's nothing slowing it down in a vacuum. The bigger the n as a number, the more there is slowing down that light. Okay, so when we take a look at our situation here, we've got air with a low n, so it's faster, and glass with a higher n, so light travels slower. Okay, so in that situation, we have our incident rays, so from Mr. Sun. Okay, and it travels through air, and in this situation, because then here's the boundary that we see, okay, light can be reflected off of this boundary, okay, but it can, because my boundary is transparent or translucent, light can also pass through. All right, and that's when light gets bent or refracted. And since we've got a difference in the index of refraction, because glass is slower, my refracted ray is going to slow down and it's going to bend towards the normal. Okay, and that's what we talked about before. So, if we have a small angle of incidence, what will happen is most of the light rays are going to refract. So that means they'll go through and very little will be reflected. But say, for instance, and I'm just going to scooch this up a bit again. Say I've got a wider angle, so a bigger incident angle, more will actually be reflected and less will be refracted. Okay, so that's kind of what we're talking about today. So just to remind you yet again, if we're going from slow to fast, in this situation that's opposite to the one we just discussed, my refracted ray will bend away from the normal and the angle will be bigger. Okay, because air is faster and it's like you took the brakes off of that light and it just went wee away. Okay, so if we take a look at a situation where we're going from slow to fast, okay, so water has a higher index of refraction compared to air. And in this situation, what will happen is, once again, because it's going from slow to fast. There's my incident ray. Here's my angle of incidence. And the refracted ray, because it's in fast, is actually bending away from the normal, so away. Okay? If we make it an even bigger angle, it's going to be refracted even further away. Okay? So that's what happens there. Never forget, these two angles are always the same, right? Because the angle of incidence equals the angle of reflection. Yeah? All right. But then, say I actually make my incident ray super far, and this refracted ray gets bent even more way if we have this special angle, and this special angle is called a critical angle. Okay, the critical angle is the actual angle of the incident ray that results in a refracted ray that actually runs along the border or the boundary between the two different mediums. So it's like it skims the surface. So it would skim the surface of the water and the air. So you don't actually see refraction and you're seeing reflection, but it's skimming the surface. If I was to have an incident ray that's bigger than C, so bigger than my critical angle, then nothing is getting refracted. Everything is getting reflected, right? And that is called total internal reflection. So your eyeballs wouldn't see anything, okay? Because everything is reflected within the body of water. Because our eyes are here. Here, I'll give us nice long eyelashes. All right? Our eyes are up here. We're not going to see anything because nothing comes out into the air. All right? So in that situation, light reflects completely off the boundary and it doesn't pass through. It does not pass through the boundary, so our eyeballs don't see it. This only happens when we go from slow to fast. Okay? So it has to go from slow to fast. And this total reflection only happens, total internal reflection only happens when my incident angle is bigger than that critical angle. And that critical angle is different for every different type of medium we're talking about. Okay? So here's another good picture where, as you can see, so I got water, which is low speed. So I'm just going to erase this. Hold up. Water has a higher N and light travels slow. Air has a smaller N and light travels fast. Okay, so don't forget, it's going from slow to fast. And as we increase our angle of incidence, the angle of refraction, which is this is the refraction part because you're going into a different medium, gets even more bent. Okay, so it moves even further away from the normal. This is a great diagram because take a look. So 15, it bends 20. 30, it bends 42. So see how it's not always the same difference? 45, it's going to bend 70. And if I bend it 60, who knows? Because we never saw it. This is beyond, this could be at the critical point, this 60, or beyond the critical angle because you get no refraction. Here's a really good video for you to watch. So we've got some examples of where you might actually see total internal reflection. So a good one is diamonds. We know that diamonds have a super high N. In fact, they're one of the highest indexes of refraction of items or substances we have here on Earth. And a lot of times, jewelers will cut diamonds in certain ways to up the internal reflection, and that's what makes them sparkly. Okay, so what ends up happening is you want the internal reflection to happen, and then you want to be able to see the sparkles. Bing, bing, bing. Sorry, that's like a creepy eye. Ooh, it almost looks like a spider. It's supposed to be an eyeball. Okay, but if you don't, and if you try and chintz out on your diamond and it's too thin, then you won't get that reflection back to your eyeball. Okay. So next, water and total internal reflection. If we take a look, so say you're standing somewhere in the water and you're looking at things and your angle of incidence is small. well, then you probably haven't hit that critical angle. So there will be refraction. However, if you're looking ahead into the distance and your angle of incidence is large, chances are you've hit the critical angle, and you have no refraction. So none of that light will bounce into your eye, and that's why you really can't see. So see how you see nothing here, but you can see the bottom here? This would be a small angle of incidence. This would be a larger angle of incidence, and it's bigger than the critical angle. Okay, so that's where we would see total internal reflection happening. So another really good example of total internal reflection and where we see it in actual place is with the use of fiber optics. Okay, and my optical fiber, so what you're going to see, so let's take a look at this right here. You've got light here, but you got no light coming out of that glass. All right, so what a fiber optic cable is made out of is a glass core. So a core like the inside, like your core inside your body, right? It's the core is made of glass, but then it's also surrounded by another casing or cladding of a different type of glass. And that cladding or casing has a different type of glass that has a smaller index of refraction. So if it has a lower index of refraction, what that means is that light travels faster. So what ends up happening is that we get total internal reflection because that light stays within the cable, but it never leaves. Okay? And that's because it's larger than the critical angle. All right? So it goes from slow to fast. Never forget that. It's got to go from the slower glass to the faster glass. All right? And we see optical fibers in phone lines. Any fiber optic cables, so phone lines, signals for TVs, data, a lot of this stuff is in use. We can actually medically use fiber optic cables in scopes, so endoscopes, colonoscopies. We learned about that in the biology unit. Okay, so these are things that are very important, and it's a useful application of total internal reflection. So once again, really good video to watch how fiber optics work. So, as always, here's some practice questions to make sure that you know what we're talking about. There's also a lesson 7 practice quiz. I want you guys to know that Miss Trombetta and we know we're not going to see you this year, and we're really sad about that. We just don't want you to give up. We want you to keep going on with these lessons. Trust me, none of it's a waste of time. Even if you decide not to do any other science, every one of these lessons has something to do with your life. Okay? I just want you to know that we miss you. We're thinking of you. If there's anything that you need help with, give us a shout, okay? Take care.